Hello and welcome. In this video, we'll be exploring two fundamental concepts in mathematics, the modulus function and rational functions. By the end of this session, you will be able to define and work with the modulus function, solve modulus equations and inequalities, and understand the key features of rational functions, including asymptotes. These topics are crucial for your IB/AAHL studies, so let's dive in. First up is the modulus function. You might also know it as the absolute value function. The modulus of a real number x, written as, is defined as its distance from 0 on the number line. Because it represents a distance, the modulus of any number can never be negative. It's always 0 or positive. Let's visualize this. For a positive number, like 7, its distance from 0 is simply 7. So the modulus of 7 is 7. Now consider a negative number, like -5. Its distance from 0 is 5 units. Therefore, the modulus of -5 is 5. This leads us to the formal algebraic definition. The modulus of x is defined as x itself if x is greater than or equal to 0, and it's defined as negative x if x is less than 0. Let's break that down. If the number inside the modulus is already positive or 0, you just keep it as it is. If the number is negative, you multiply it by -1 to make it positive. This is why -5 becomes -5, which is 5. An equivalent and very useful definition is that the modulus of x is the square root of x squared. This definition is particularly helpful in proofs. For example, the modulus of 7 is the square root of 7 squared, which is the square root of 49, or 7. The modulus of -5 is the square root of -5 squared, which is the square root of 25, or 5. Both definitions give us the same result. Now let's see how to apply this definition to evaluate expressions. We'll work through a few examples. Suppose we are given that a equals -3 and b equals 4. We need to find the value of three expressions. For part A, we need to find the modulus of 7 plus a. We substitute the value of a into the expression. This simplifies to the modulus of 4. Since 4 is a positive number, its modulus is just 4. So the answer is 4. Next, for part B, we need to find the modulus of a times b. We substitute the values of a and b. This gives us the modulus of -12. Since -12 is a negative number, its modulus is positive 12. The answer is 12. Finally, for part C, we need to find the modulus of a squared plus 2b. Let's substitute the values. -3 squared is 9, and 2 times 4 is 8. So we have the modulus of 9 plus 8, which is the modulus of 17. The modulus of 17 is 17. The answer is 17. As you can see, the process is to first evaluate the expression inside the modulus bars, and then apply the modulus definition to the result. Let's try another one. This time, let's find the value of the modulus of 3 minus 2x minus x squared, when x equals -3. We substitute x equals -3 into the expression. -2 times -3 is positive 6. -3 squared is 9. So we have the modulus of 3 plus 6 minus 9. This simplifies to the modulus of 0, which is 0. The answer is 0. Now let's look at the graph of the modulus function. The relation y equals the modulus of x is a function, and its graph is a very recognizable V-shape. The graph of y equals the modulus of x is a V-shape with its vertex at the origin, 0, 0. We can understand this graph by looking at our algebraic definition. For x values greater than or equal to 0, the function is y equals x. This is just a straight line with a slope of 1, starting from the origin and going up to the right. For x values less than 0, the function is y equals -x. This is a straight line with a slope of -1, starting from the origin and going up to the left. So, the graph is formed by these two pieces. The key takeaway is that the graph is always above or on the x-axis, because the modulus function never produces a negative output. Let's try graphing a more complex function, f of x equals x minus the modulus of x. We'll use the algebraic definition to break it down. First, consider the case where x is less than 0. In this case, the modulus of x is -x. So, f of x becomes x minus -x, which simplifies to 2x. Next, consider the case where x is greater than or equal to 0. Here, the modulus of x is just x, so f of x becomes x minus x, which is 0. So our function can be written as a piecewise function. F of x equals 2, x for x less than 0, and 0 for x greater than or equal to 0. To graph this, we draw the line y equals 2x for all negative x values, and we draw the line y equals 0, which is the x-axis, for all non-negative x values. The result is a graph that is the x-axis for x greater than or equal to 0, and a line with a slope of 2 for x less than 0. Let's explore another example of graphing a function involving modulus. This time we'll graph f of x equals x times the modulus of x. Again, we'll use the piecewise definition. First, for x less than 0, the modulus of x is negative x, so f of x becomes x times negative x, which is negative x squared. Next, for x greater than or equal to 0, the modulus of x is x. So f of x becomes x times x, which is x squared. So our function is x squared for x greater than or equal to 0, and negative x squared for x less than 0. To graph this, we draw the right half of the parabola y equals x squared, and the left half of the parabola y equals negative x squared. The result is a curve that looks like a cubic function, but is actually made of two parabolic pieces. This method of breaking the function into cases based on the sign of the expression inside the modulus is a powerful technique for graphing and analyzing these functions. Let's now look at some important properties of the modulus function. These properties are essential for solving equations and inequalities. First, the modulus of any number is always greater than or equal to 0. This is because it represents a distance. Second, the modulus of negative x is the same as the modulus of x. For example, the modulus of minus 5 is 5, and the modulus of 5 is also 5. Third, the square of the modulus of x is equal to the square of x. This is a direct consequence of the definition $equals SQRT dat x squared $. Fourth, the modulus of a product is the product of the moduli. This means you can split the modulus over multiplication. Fifth, the modulus of a quotient is the quotient of the moduli, provided the denominator is not 0. You can also split the modulus over division. Sixth, the modulus of x minus y is the same as the modulus of y minus x. This property is very intuitive if you remember that modulus represents distance. The distance from x to y is the same as the distance from y to x. These properties are powerful tools. For instance, the property $² equals x squared $, is often used to solve modulus equations by squaring both sides, which eliminates the modulus bars. Now let's apply these ideas to solve modulus equations. The key principle is that if the modulus of an expression equals a positive number, the expression itself must be equal to that number or its negative. In other words, if the modulus of x equals a, where a is a positive number, then x must be equal to positive a or negative a. Let's solve the equation. The modulus of 2x plus 3 equals 7. Using our rule, the expression inside the modulus, 2x plus 3, must be equal to positive 7 or negative 7. This gives us two separate linear equations to solve. First, 2x plus 3 equals 7. Subtracting 3 from both sides gives 2x equals 4, so x equals 2. Second, 2x plus 3 equals negative 7. Subtracting 3 gives 2x equals negative 10, so x equals negative 5. Our solutions are x equals 2 or x equals negative 5. It's always a good idea to check your answers. If x equals 2, 2 plus 3 equals 7 equals 7. If x equals minus 5, 2 minus 5 plus 3 equals minus 7 equals 7. Both are correct. Now what about an equation like the modulus of 3 minus 2x equals negative 1? Remember our first property. The modulus of any number is always non-negative. It can never be negative. Therefore, the left-hand side of this equation, the modulus of 3 minus 2x, can never be equal to the right-hand side, which is negative 1. This equation has no solution. Let's tackle equations where the modulus is on both sides, or where the expression is a fraction. Consider the equation. The modulus of 3x plus 2, all over 1 minus x, equals 4. We can use the property that the modulus of a quotient is the quotient of the moduli. This means the modulus of 3x plus 2 divided by the modulus of 1 minus x equals 4. We can then multiply both sides by the modulus of 1 minus x. Now we have an equation with moduli on both sides. A general rule for this is that if the modulus of a equals the modulus of b, then a equals plus or minus b. So 3x plus 2 must equal plus or minus 4 times the quantity 1 minus x. This gives us two cases. Case 1 to 3x plus 2 equals 4 minus 4x. Rearranging gives 7x equals 2, so x equals 2 over 7. Case 2 to 3x plus 2 equals negative 4 plus 4x. Rearranging gives 6 equals x. So our solutions are x equals 2 over 7 or x equals 6. Let's look at another example of moduli on both sides. Solve the modulus of x plus 1 equals the modulus of 2x minus 3. Using our rule, x plus 1 must equal plus or minus the quantity 2x minus 3. Case 1. X plus 1 equals 2x minus 3. Rearranging gives 4 equals x. Case 2. X plus 1 equals negative 2x plus 3. Rearranging gives 3x equals 2, so x equals 2 over 3. Our solutions are x equals 4 or x equals 2 over 3. Now let's move on to modulus inequalities. The rules for inequalities are slightly different. First, if the modulus of x is less than a positive number a, then x must be between negative a and positive a. Think of it as x being within a distance of a from 0. Second, if the modulus of x is greater than a positive number a, then x must be less than negative a or greater than positive a. This means x is further than a distance of a from 0. Let's solve an inequality using these rules. Solve the modulus of 2x minus 1 is less than 3. Using our first rule, the expression inside the modulus, 2x minus 1, must be between negative 3 and positive 3. To solve this compound inequality, we perform the same operation on all three parts. First, add 1 to all parts. This gives negative 2 is less than 2, x is less than 4. Next, divide all parts by 2. This gives negative 1 is less than x is less than 2. So the solution is x is between negative 1 and 2. Let's try one with a greater than sign. Solve the modulus of 3 minus 4x is greater than 2. Using our second rule, the expression 3 minus 4x must be less than negative 2 or greater than positive 2. We solve these two inequalities separately. For the first one, 3 minus 4x is less than negative 2. Subtracting 3 gives negative 4x is less than negative 5. Dividing by negative 4 and reversing the inequality sign gives x is greater than 5 over 4. For the second one, 3 minus 4x is greater than 2. Subtracting 3 gives negative 4x is greater than negative 1. Dividing by negative 4 and reversing the inequality sign gives x is less than 1 over 4. So, the solution is x is less than 1 over 4, or x is greater than 5 over 4. Sometimes, solving modulus inequalities algebraically can be complicated. In these cases, a graphical method can be very effective. Let's solve the inequality. The modulus of 1 minus 2x is greater than x plus 1, using a graphical approach. The strategy is to graph the left-hand side, y equals the modulus of 1 minus 2x, and the right-hand side, y equals x plus 1, on the same set of axes. Let's start with the line y equals x plus 1. It has a y-intercept of 1 and a slope of 1. Now for the modulus function. The expression inside is 1 minus 2x. This is 0 when x equals 1/2. So the vertex of the v-shape is at x equals 1/2. When x is greater than 1/2, 1 minus 2x is negative, so the function is negative 1 to 2x equals 2x1. When x is less than 1/2, 1 minus 2x is positive, so the function is 1 to 2x. Now we look for the points where the two graphs intersect. We can find these algebraically by setting the two functions equal to each other. We solve the equation, the modulus of 1 minus 2x equals x plus 1. This gives us two cases, 1 minus 2x equals x plus 1, which solves to x equals 0, and 1 minus 2x equals negative x minus 1, which solves to x equals 2. So the graphs intersect at x equals 0 and x equals 2. The corresponding y values are 1 and 3. The original inequality was 1 to 2x greater than x plus 1. This asks, for which x values is the graph of y equals 1 to 2x above the graph of y equals x plus 1? Looking at the graph, we can see that the V shape is above the straight line for x values to the left of 0 and for x values to the right of 2. So the solution is x is less than 0 or x is greater than 2. Let's move on to our second major topic, rational functions. A rational function is essentially a fraction where the numerator and denominator are both polynomials. In this course, we'll focus on a specific type, functions of the form y equals ax plus b all over cx plus d, where c is not 0. The most important feature of rational functions is the presence of asymptotes. Asymptotes are lines that the graph of the function gets closer and closer to, but never actually touches. The simplest example is the reciprocal function, y equals 1 over x. Its graph is a rectangular hyperbola. Let's look at its graph. Notice that the function is undefined when x equals 0, because you can't divide by 0. As x gets very close to 0, the value of y gets very large, either positive or negative. This creates a vertical asymptote at the line x equals 0, which is the y-axis. Now, what happens as x gets very large, either positive or negative? As x approaches infinity, 1 over x approaches 0. The graph gets closer and closer to the x-axis, but never reaches it. This creates a horizontal asymptote at the line y equals 0, which is the x-axis. So the graph of y equals 1 over x has two asymptotes, a vertical one at x equals 0, and a horizontal one at y equals 0. Let's investigate how the constant, k, affects the graph of a reciprocal function y equals k over x. We'll start by looking at positive values of k. Let's compare the graphs of y equals 1 over x, y equals 2 over x, and y equals 4 over x. As you can see, all three graphs are in the first and third quadrants. As k increases, the branches of the hyperbola move further away from the origin. The asymptotes remain the same at x equals 0 and y equals 0. Now let's consider negative values of k. Let's compare y equals negative 1 over x, y equals negative 2 over x, and y equals negative 4 over x. When k is negative, the branches of the hyperbola are in the second and fourth quadrants. As the absolute value of k increases, the branches again move further from the origin. The asymptotes are still x equals 0 and y equals 0. So the sign of k determines which quadrants the graph is in, and the magnitude of k determines how far the branches are from the origin. Let's now look at the general form of a rational function, y equals ax plus b over cx plus d, and learn how to find its asymptotes. Consider the function f of x equals 2x plus 1 all over x minus 1. To find the vertical asymptote, we look for the x value that makes the denominator 0. This is where the function is undefined. Setting the denominator x minus 1 equal to 0 gives us x equals 1. So the vertical asymptote is the line x equals 1. To find the horizontal asymptote, we consider the behavior of the function as x approaches positive or negative infinity. As x gets very large, the constant terms, 1 in the numerator and minus 1 in the denominator, become insignificant compared to the x terms. The function behaves like 2x over x, which simplifies to 2. So the horizontal asymptote is the line y equals 2. Let's look at the graph. You can see the vertical asymptote at x equals 1, and the horizontal asymptote at y equals 2. The graph approaches these lines, but never touches them. A quick way to find the horizontal asymptote for this form is to take the ratio of the coefficients of x in the numerator and denominator. Here, it's 2 over 1, which is 2. Let's work through a complete example of analyzing and sketching a rational function. Consider the function y equals 6 over x minus 2 plus 4. We'll find its asymptotes, intercepts, and sketch the graph. First, the asymptotes. The vertical asymptote occurs when the denominator is 0, so x minus 2 equals 0, which means x equals 2. The horizontal asymptote is determined by the constant term added to the fraction, which is y equals 4. Next, the intercepts. To find the x-intercept, we set y equal to 0. This gives 0 equals 6 over x minus 2 plus 4. Subtracting 4 and multiplying by x minus 2 gives negative 4, x plus 8 equals 6. Solving for x gives x equals 1/2. To find the y-intercept, we set x equal to 0. This gives y equals 6 over negative 2 plus 4. This is negative 3 plus 4, which equals 1. So the y-intercept is 1. Now we can sketch the graph. We draw the asymptotes at x equals 2 and y equals 4. We mark the intercepts at 1/2, 0, and 0, 1. Since the numerator is positive, the branches of the hyperbola will be in the top right and bottom left regions relative to the asymptotes. We draw the curves passing through our intercepts and approaching the asymptotes. Finally, let's look at two important inequalities involving modulus that you should be familiar with. The first is the triangle inequality, which states that the modulus of x plus y is less than or equal to the modulus of x plus the modulus of y. This inequality is true for all real numbers x and y. It's called the triangle inequality because it has a geometric interpretation related to the lengths of the sides of a triangle. Let's prove it. We know that squared equals x squared. So x plus y squared equals x plus y squared equals x squared plus 2xy plus y squared. We also know that xy is always less than or equal to xy, which is equal to. Substituting this into our expression, we get that x plus y squared is less than or equal to x squared plus 2 plus y squared, which is the same as plus y squared. Taking the square root of both sides gives us the triangle inequality. The second inequality is the reverse triangle inequality, which states that the modulus of x minus the modulus of y is less than or equal to the modulus of x minus y. This inequality is also true for all real numbers x and y. It's a direct consequence of the triangle inequality. Let's quickly recap what we've covered today. These concepts are foundational for more advanced topics in calculus and analysis. Now, to solidify your understanding, here are some practice questions. All right, let's reveal the answers. Here are the solutions. Check your work carefully. If you made a mistake, go back and review the relevant section of the video. Thank you for watching.